tēnā koutou katoa. Ko tuki tuki, toko awa. Ko taki timu, toko waka. Ko aiparaki, toko moana. Ko Ngāti Kahununu, toko iwi. No Napier, aho. Ko Tremain, toko whānau. Ko Edu, toko ingoa. No reira, tēnā koutou, tēnā koutou, tēnā koutou katoa. Kia ora, my name is Edu Tremain, and I'm here to tell you about the polluted water problem we have in New Zealand. Previously, I introduced myself to you all with my pepeha. Did you notice how many of the sentences in my pepeha related to water? My pepeha involves stating my ocean, moana, river, awa, and waka, which travels along our waterways. The importance of why, the te reo Māori word for water, in Māori culture is apparent. Seafood was also a major part of the native Māori diet, as they used flax nets, traps, and hooks to catch the various fish around New Zealand. In Māori mythology, the god of the sea, Tangaroa, was one of the most powerful gods. Not to mention, Maui's greatest adventure took place in the ocean, by casting his jawbone and catching Te Ika a Maui, the North Island. To witness the sea life slowly being decimated in New Zealand due to pollution must be causing unimaginable grief within our tangata whenua. When I was a kid, a typical weekend for me was going to the Clyde River between Napier and Hastings and jumping off the bridge into the river. These days the water is far too polluted and swimming in the river is prohibited. This is the case for countless New Zealanders who have had the privilege of swimming in their local rivers stripped away from them by the byproducts of our production industries. Pollutants are also entering our town water supplies. This is from rain, passing through the polluted air. The pollutants are carried down with the rain and into our soil. The pollutants in rainwater seep through the soil and into our water supplies. This is obviously a place that we do not want these toxic pollutants. My presentation suggests a clean, green, effective solution to this problem. A way of breaking down these pollutants into non-hazardous compounds and ions. Green chemistry is a recently started branch of science that is going to be paramount in the next few years. Green chemistry involves using chemical processes and reactions to reduce or eliminate harmful substances we have released into the environment. Water has countless applications in our day-to-day lives, from keeping us clean to being an essential part of survival for every organism on Earth. Water is a limited resource and needs to be preserved for future generations. Water pollution, occurring mainly from industrial waste, is a cause for concern, and if not acted on correctly, will have serious consequences for us as a species. At present, chlorination is being used to try to eliminate the hazardous chemicals in our waterways. It has been a big help in lowering disease rates and keeping us safe. However, chlorination is known to release toxic organic chlorides. These toxic organic chlorides were originally fine for humans to consume and had minimal effects on the environment. After 120 years of using this method, however, the number of toxic organic chlorides in our water supply has built up and we are starting to see the effects. Chlorination can also cause our tap water to have an off-putting taste and smell. The main trihalomethane disinfectant byproducts, DBPs, that the chlorination process creates are chloroform, bromodichloromethane, chlorodibromomethane, and bromoform. These byproducts of chlorination are carcinogenic, meaning they can cause cancer. Studies done on rats and humans have proven that these DBPs, when consumed, severely increase the risk of cancer in the liver, kidney, and intestine. These byproducts do not break down, meaning the risks are only increasing as more and more of these trihalomethanes enter our water supply. The chlorination process is also unable to deal with dioxin contamination of some herbicides, specifically 2,4,5-trichlorophenoxyacetic acid, which is used for killing broadleaf plants. Rainwater washes the herbicide from soil and into our water. It is proven to cause much human illness and even severe abnormalities in New Zealand infants. These facts point to what I believe to be an obvious conclusion, that the future of water purification must not rely on a method used since the 1800s. Now that we are aware of its harmful long-term effects, we must adapt and switch to a cleaner, greener method. The solution is near with the use of green chemical oxidation procedures. The use of green chemical oxidation procedures for the purification of water has been a heavily researched topic in recent years. The problems with these methods tends to be the large activation energy barriers required for these non-spontaneous reactions to occur. However, due to a massive breakthrough in oxidation catalysts by New Zealand-born American scientist Terence J. Collins, the solution is here. Terence J. Collins has created tetramido-macrocyclic ligands, or TAMLs for short, an iron-based catalyst that are hundreds of times smaller than the enzymes previously used, making the production of the catalyst significantly cheaper and easier. For those of you unsure what a catalyst is, just think of it as Tinder for compounds, an old-fashioned matchmaker. The idea of the TAML came from enzymes called peroxidases. The enzymes are found in forests on rotting trees. Their purpose is to catalyze oxidation reactions containing hydrogen peroxide. The peroxidases cause hydrogen peroxide to break down polymers in rotting wood into smaller molecules that are then able to be absorbed by the fungi. Terence J. Collins wondered if the concept of breaking down compounds through oxidation reactions could help us remove pollutants from our water. The peroxidases were far too complex and large to be any use commercially. As such, the TAML was created. Nature had the solution all along. We just had to go and find it. Hydrogen peroxide, H2O2, is a strong oxidizing agent that when paired with TAMLs can fully destroy many pollutants in a matter of seconds. Hydrogen peroxide contains both hydrogen and oxygen, which are both very reactive elements. Reactions containing oxygen are very destructive due to the strong bonds created, especially with hydrogen. As such, hydrogen peroxide in water creates what is referred to by scientists as liquid fire that demolishes carbon-containing molecules around it. The TAML had to be durable enough to survive this liquid fire. The TAML structure consists of a central iron atom bonded to 4 nitrogens. Surrounding that are carbon rings linked to form an outer ring called the macrocycle. This outer ring provides stability to the molecule and allows the molecule to survive the reactions it creates. The TAMLs also contain a water ligand, a ligand being a functional group which is bonded to the central iron atom. The macrocycle was the key to the successful catalyst. It took Terence J. Collins 15 years to perfect the carbon rings. It had to be the perfect balance between creating a strong firewall but not letting it be indestructible. The TAML had to be strong enough to endure the violent reactions it creates, but not be indestructible and create a pollution problem of its own. Not too hot, not too cold. As they would refer to in Te Reo, taurete, balance. When TAMLs are in a solution with pollutants and hydrogen peroxide, the hydrogen peroxide replaces the water ligand. The peroxide ligand then discards both its hydrogen atoms and one of its oxygen atoms in the form of water, leaving behind a negatively charged oxygen. The oxygen being more electronegative than the iron causes the electrons to be pulled closer to the oxygen, resulting in a larger positive charge on the iron. This means that the TAML is reactive enough to extract electrons from oxidizable pollutants. The strong positively charged iron breaks down pollutants into non-hazardous compounds and ions. The chemical formula of these reactions is as shown in the PowerPoint. The oxidation reaction turns the substrate, which in these cases are toxic pollutants, into the product, non-hazardous compounds and ions. The reaction also causes the TAMLs to become inactive. The recently developed relationship, under the chemical formulas in the PowerPoint, can be used to calculate the change in concentration of active TAMLs in moles per litre. The S stands for the concentration of the substrate. K2 refers to the product concentration. K1 is the inactive catalyst concentration, and Fe3 is the total concentration of iron in the solution. This formula measures the amount of TAMLs used in the reaction, which will be very useful for sustainable TAML use in the future. There have been numerous experiments proving the effectiveness of TAMLs in peroxide, as they destroy many durable pollutants. One of which was chlorophenols, specifically 2,4,6-trichlorophenol, and pentachlorophenol. Environmental pollutants released into the water as a byproduct of our chemical and pharmaceutical industries. Chlorinated phenols are resistant to microbiological degradation and can live in the environment for decades. However, TAMLs are found to degrade the compounds completely in a matter of minutes. The pulp and paper industry produces over 100 million tonnes of bleached pulp every year, which is turned into paper. Among other pollutants, the process creates a coffee-coloured liquid waste. This liquid waste stains the waterways and stops light from entering the water. Large ecosystems of aquatic life that depend on photosynthesis and survival of aquatic plants are severely affected. Studies have been done at pulp mills in New Zealand and the United States of America to show the effect of TAMLs on the pollutant. These studies have shown that injecting TAMLs into exit pipes and pulp treatment towers decrease the effect of staining by up to 78%. Heterogeneous bleaching is the most effective method for adding the TAML catalyst to hydrogen peroxide and polluted water solution. It involves embedding the iron-based TAML into a polymer film and adding the solid support into the solution. The application of this method to water purification plants can be used as shown in my presentation. The TAML polymer film is the functionalized membrane which is inserted between the hydrogen peroxide and polluted water. The hydrogen peroxide also acts as a buffer, meaning its pH rarely changes as acids or bases are added to it. Toxic compounds pass by the TAML film and are quickly turned into harmless oxidized compounds. TAMLs have proven successful in destroying various toxic pollutants found in our water supply, such as herbicides, insecticides, animal waste and medicine from wastewater of the farming industry, coloured lignin fragments and organic chlorides from the pulp and paper industry, dyes, cosmetics and drugs found in sewage, and the various toxic pollutants created in the production of dyes in the textile industry, many of which have polluted our waterways for centuries, and it is time to combat these unbreakable pollutants. Using TAMLs and peroxide for the disinfection of water is looking promising, since it has passed all of its toxicity tests with flying colours. However, with all new chemical processes, caution must be taken before making the change. There is always the possibility of unseen side effects of new compounds entering our water. I believe the TAML and peroxide combo has huge potential and is the key to a safe, sustainable future. Our tangata whenua will once again be able to live peacefully in Rainga as we fix the mess we created.